All right, welcome back to Talk Tensors. We got a really cool paper to deep dive into today.
Yeah, this one's a good one.
This one really caught our eye.
It did.
It's all about how to make these big, powerful LLMs, these large language models, even better at reasoning,
Okay.
especially when things get really complicated. And the approach they're taking is fascinating. They're combining something called conformal language modeling, that's CLM, with answer set programming, or ASP.
Right, and it's a really smart way to address some of those limitations we've been seeing with LLMs when it comes to, those multi-step reasoning tasks, those really complex scenarios where a single wrong step can throw off the whole process.
Exactly. I mean, we've all seen how impressive LLMs are at generating text. They can write stories, translate languages, even hold conversations that could be eerily human-like.
Yeah, they're really good at mimicking the way we use language.
But when you get into these situations where you need them to perform a series of logical deductions, especially when it involves understanding how things are arranged in space, that's where things can start to get a little shaky.
Yeah, their reliability can really take a hit. You ask them the same question multiple times, you might get a different answer each time, and that's a big problem for a lot of real-world applications where you need that consistency and robustness.
Absolutely. And that's precisely where this paper comes in. So instead of trying to somehow make the LLM itself inherently better at reasoning, which is a pretty tall order to begin with, what they're doing is giving it this external framework to work with.
It's like giving it a structured scaffold, a logical backbone, built using this powerful tool called answer set programming.
Right, and ASP is all about representing knowledge and relationships in a very clear, logical way. So instead of the LLM directly spitting out an answer, which can be a bit of a black box, we don't always know how it got there.
Yeah, it can be hard to trace the reasoning process.
They're using CLM to generate a set of potential ASP programs, kind of like giving the LLM a toolkit of logical building blocks. And the really clever part is...
Well, statistical guarantees.
The guarantees.
Yeah.
Right. CLM, because it's rooted in this statistical framework called conformal prediction, provides these guarantees that at least one of those ASP programs in the set is going to lead to the correct answer.
It's like a safety net, ensuring you don't fall through the cracks of uncertainty.
Exactly. Think about it for applications where reliability is absolutely paramount, like, well, I don't know, let's say robotics or autonomous vehicles.
That's medical diagnosis even.
Yeah, or even medical diagnosis, right?
Yeah.
That kind of guarantee is a game changer.
Absolutely. It could really increase trust and adoption of LLM-based systems in those high-stakes domains.
So they tested all this out using the step game dataset, which was designed specifically to challenge spatial reasoning abilities. Imagine trying to describe the location of something by giving directions like go 2 steps north, then 1 step east, and so on. That's essentially what step game's all about.
Right, and it's a really good test bed because those spatial relationships can get pretty complex, especially when you start adding more steps, more directions, more objects.
And their key finding was that by using this CLM-ASP combo, they saw a really significant improvement in the accuracy of those LLMs on these reasoning tasks, compared to the standard method of just letting the LLM sample answers on its own.
Yeah, we're talking a 20% improvement, sometimes even more. That's a huge jump in reliability, especially when you're dealing with tasks that have real-world consequences.
Okay, so let's take a closer look at the paper itself. It starts by laying out this need for automated reasoning systems, right? We want AI systems that can understand and reason about the world.
Solve problems, make decisions, just like we do.
Exactly. And while LLMs have shown amazing potential in many areas, they still struggle with that robust, verifiable reasoning, especially when multiple steps are involved.
Yeah, they can be inconsistent, and sometimes they make mistakes that are just baffling, considering how well they can perform on other tasks. It's like they have these pockets of brilliance, but also these surprising blind spots.
Right, and the paper does a really good job of illustrating that. They point to examples where LLMs give different answers to the same question, and the reasoning process itself can be opaque. You don't always know why they arrived at a particular conclusion.
And that's a major obstacle for building truly trustworthy AI systems. We need to understand not just what the AI is saying, but also how it arrived at that conclusion.
Absolutely. And that's where the paper highlights the potential of this idea of neurosymbolic AI.
Neurosymbolic AI.
Yeah, so neurosymbolic AI is all about combining the strengths of two major approaches to artificial intelligence. The connectionist approach, which is what neural networks are all about.
Right, learning from data, patterns, connections.
Exactly. And the symbolic approach, which is where you have these explicit rules, symbols, logic. Answer set programming, or ASP, is a prime example of that symbolic approach.
So it's like trying to merge the intuition and flexibility of neural networks with the precision and transparency of logic.
Exactly. It's about getting the best of both worlds. And in this paper, ASP is the key to providing that logical framework for the LLM to reason within.
So instead of just generating text directly, the LLM is now tasked with translating the problem into this formal ASP language.
Right. But, as the paper points out, this translation process itself is not without its challenges. LLMs can make mistakes. They can misinterpret the problem. And they can generate ASP code that is flawed or doesn't accurately capture the nuances of the original task.
Yeah, it's a potential bottleneck.
Exactly. And that's where conformal language modeling, or CLM, steps in to provide a solution. It builds upon the foundation of conformal prediction, which is this really interesting statistical framework designed to give you guarantees about the reliability of predictions.
And that's something we don't often see in machine learning, right? Guarantees.
Right. It's almost too good to be true. But the core idea behind conformal prediction is that you can look at past data and use it to estimate the uncertainty in your future predictions. So instead of just saying, okay, this is the most likely outcome, you're saying, okay, here's a set of possible outcomes, and I'm confident that the true outcome will be within this set with a certain probability.
It's like drawing a boundary around your predictions, acknowledging that there's always a chance of being wrong, but controlling how wrong you might be.
Exactly. And CLM takes this concept and applies it specifically to the realm of language models. So instead of just predicting the single most likely next word, it generates a whole set of plausible responses. And the statistical theory tells us that at least one of those responses in the set, the so-called conformal set, is going to be correct or at least acceptable.
Right. And the goal is to control the risk that none of the generated responses are good enough based on whatever criteria you define for the task.
Exactly. And at the same time, you want to make sure that set of responses is as useful as possible. So you're trying to maximize the quality of each individual response, ensuring there's diversity in the set and having a high overall confidence that you've captured the correct answer within that set.
And the paper makes this really interesting observation.
Yeah.
Most of the work on CLM so far has focused on those natural language generation tasks, where it's a little fuzzy what a correct answer actually is. Applying it to this much stricter domain of formal languages like ASP allows for a much clearer evaluation of how well CLM actually performs.
It's a much more rigorous test.
It is.
So we have the LLM taking a step game problem, feeding it through CLM, and getting a set of potential ASP programs as output. How does CLM actually decide which of those programs get included in that final conformal set? What's the selection process like?
So it's a calibrated rejection sampling process. The LLM starts by generating a bunch of candidate ASP programs based on the input, and then an admission function steps in and filters out any programs that are just blatantly unusable, like ASP code that has syntax errors and wouldn't even run properly in the solver.
It's like a quality control check right at the beginning.
Exactly. Get rid of the obvious junk. For the remaining programs that are at least syntactically valid, CLM evaluates them based on three main factors: quality, diversity, and confidence.
Quality, meaning how well each individual program seems to capture the problem. Diversity, meaning you don't have a bunch of programs that are all basically the same but with minor variations. And confidence, meaning how sure the model is that the set as a whole contains a correct solution.
Right. And these three factors are all controlled by these parameters called lambda, which are basically weights that determine how much emphasis to put on each factor during the selection process.
And those lambda parameters are not just arbitrary values, right? They're learned through this calibration process.
Exactly. That's a key part of CLM. The researchers used a separate portion of their data, the calibration set, to find the optimal values for those lambda parameters. They essentially experiment with different combinations of those values and see how well they perform in terms of ensuring that the resulting conformal sets contain the correct answers.
So it's like a fine-tuning process.
It is. It is. And the goal is to find that sweet spot where you have a high probability of having the correct answer in your set, but the set itself isn't so huge that it becomes computationally impractical to work with. It's a balance between reliability and efficiency.
So after all this calibration is done, the system is ready to tackle those brand new step game problems, right?
Yep. Yeah.
The LLM generates a set of ASP programs using CLM. That set is filtered based on those calibrated Lambda parameters, and then those programs are given to the ASP solver, which is called Klingo in this case.
And if at least one of those ASP programs in the set produces the correct answer to the step game problem, that's a win.
A win for Neurosymbolic AI.
That's right. And one thing that really stood out to me in the paper was their choice of LLMs. They specifically decided to work with these mid-range, publicly available models rather than those massive proprietary ones that only a few companies have access to.
I noticed that too, and I think that's a really important point. They're showing that this combination of ASP and CLM can significantly improve the reasoning abilities of these more accessible LLMs, which is great news for the research community and anyone who wants to build applications using these technologies.
It democratizes the field a bit, making it more accessible to researchers and developers who don't have the resources to train or access those giant models.
Exactly. And they also explored how the choice of calibration set affects the performance of the system. They compared using a diverse set of examples with different levels of complexity to using a set that only contained simpler examples, just to see how well the system could generalize to new challenges.
That's really important, right? Understanding how the calibration process influences the overall performance and generalizability of the system.
Absolutely. And of course, step game is a really good benchmark for all of this because it forces the models to perform these multi-step logical deductions based on spatial relationships. It's not just about understanding individual words or sentences, it's about grasping the underlying meaning and the spatial logic.
Right. And by varying the number of hops in those spatial relationships, they can really crank up the complexity dial and see how well the system holds up.
So the paper describes two main experiments they conducted. The first one used some of those standard NLP metrics like row shell to assess the diversity of the generated ASP programs.
Which makes sense to some degree, right? OJ is often used to evaluate things like summarization, where you're looking at how well the generated text captures the key information from the original source. So you could argue that a diverse set of ASP programs should be better at covering all the bases, all the potential ways to represent the problem logically.
Right. But they also recognize that these standard text similarity metrics might not be the best way to judge whether an ASP program is actually logically sound and will lead to the correct answer. So for the second experiment, they came up with this really clever idea. They used another LLM, a more powerful one, that they fine-tuned specifically for this task, as a judge to evaluate the quality of the generated ASP code.
An LLM as judge. That's brilliant. So instead of relying on these generic text metrics, they trained a separate LLM to actually understand the semantics and the logic of ASP code.
Exactly. This judge model was trained to recognize patterns in the ASP code that indicate whether it's likely to be correct or not, going beyond those superficial text similarities that a metric like Roge would focus on.
It's like having an expert programmer look at the code and say, yeah, this makes sense, it's well structured, it's likely to produce the right results, or no, this is all messed up, there are logical errors here, it's not going to work.
Exactly. And the results were really interesting. They found that this LLM as judge metric was much more consistent and provided a more accurate measure of improvement, especially for those more complex reasoning tasks.
It really highlights that when you're dealing with formal languages like ASP, you need evaluation methods that understand the underlying logic, not just how similar the words are.
Absolutely. And so what did they find in terms of overall performance?
Well, in that first experiment, using CLM resulted in a significant boost in accuracy across all the test sets compared to the baseline of just letting the LLM sample answers directly.
And they also found that calibrating CLM with that more diverse set of examples, those with varying levels of complexity, led to better performance across a wider range of reasoning difficulties.
Right. But they did notice a drop-off in performance when they tested the system on those really long 15-step reasoning problems, suggesting that there are still some limitations in how well the system generalizes to tasks that are much more complex than what it was trained on.
Right. There's always room for improvement. But even with that drop-off, the results are still really impressive.
Oh, absolutely. They showed that CLM can significantly enhance the reasoning capabilities of these mid-range LLMs. And the second experiment, using that LLM as judge metric, really reinforced that finding, showing even greater improvements for the more complex problems.
And one of the most valuable parts of the paper, I thought, was their error analysis. They went through and categorized the different types of mistakes the LLM makes when it's trying to generate that ASP code from natural language.
Yeah, that's always really insightful. Understanding the types of errors that occur can help you pinpoint weaknesses in the system and guide future research.
Exactly. So what were some of the most common errors they observed?
Well, the most frequent problem they ran into was the ASP solver, Klingo, just returning an empty result, meaning it couldn't even execute the generated code.
So a total failure to launch.
Exactly, and this could happen for a number of reasons. They found instances where the LLM included incorrect facts in the ASP code, where there were typos in the rules of the program, and even cases where the LLM kind of got confused and tacked on some random natural language text at the end of the code, which, of course, the solver couldn't understand.
It's like it got lost in translation between natural language and this formal logic language.
Right, exactly. Another common error was that Klingo would produce a single answer set, but it would be missing the correct answer to the original step game problem.
So it's like it went through the reasoning process, but somewhere along the way, it missed a crucial piece of information or made a wrong turn.
Yep. And they also saw cases where the ASP program would produce one answer set, but it would contain multiple possible answers when there should have only been one definitive answer.
Like it couldn't quite narrow down the possibilities.
Right. And this usually happened because of errors in the rules that were defined in the ASP program, so the logic itself was flawed. They also found instances where the program would give a single answer set with a single answer, but it was the wrong answer, often due to a mistake in translating the natural language into ASP logic.
And finally, they observed situations where the LLM would accidentally generate multiple facts for what was intended to be a single instruction in the natural language, which would then lead to multiple answer sets when only one was expected.
Right, and that often happened when there were multiple items listed in the natural language instruction separated by commas. The LLM would treat each item as a separate fact, leading to this overgeneration of ASP code.
So it's like it was being a little too literal, a little too eager to translate every little detail.
Exactly. And all of these errors, while they're frustrating, they're also incredibly valuable because they really pinpoint those specific challenges that LLMs face when they're trying to bridge that gap between natural language and formal logic.
It's like they're giving us a roadmap for future research, showing us where we need to focus our efforts to make these systems more reliable and robust.
Absolutely. And the paper wraps up by emphasizing those significant improvements that CLM brings to the table, especially when you pair it with a more appropriate evaluation metric like their LLM as judge approach.
And they highlight the importance of having a diverse set of examples in the calibration data for CLM.
But they're also upfront about the limitations. The challenge of generalizing to reasoning tasks that are far more complex than what the system was calibrated on is still a major hurdle.
Right. It's a reminder that this field is still very much in its early stages. But even with those limitations, this research feels like a really significant step towards building more trustworthy and dependable AI systems for these complex reasoning tasks.
Oh, absolutely. It's pushing the boundaries of what's possible with LLMs.
So stepping back a bit, what are some of the real-world implications of this research? Where could we see this kind of technology being applied to make a real difference?
I mean, the possibilities are pretty vast. In medicine, for example, imagine an AI system that can not only analyze patient data and suggest potential diagnoses, but also provide a measure of confidence in its reasoning, backed by statistical guarantees. That could be incredibly valuable for doctors, helping them make more informed decisions.
Right. And it feels like logistics or manufacturing, where you have these really complex planning and scheduling problems with lots of constraints to consider. This kind of AI could lead to much more efficient and optimized solutions.
And even in areas like software or hardware verification, where ensuring the correctness and reliability of systems is paramount, this neurosymbolic approach could offer a new level of rigor and assurance.
And for anyone working with large knowledge bases, having an AI that can answer complex queries with a higher degree of accuracy and a quantifiable level of confidence would be huge.
Absolutely. It's about making AI systems that are not just smart, but also trustworthy, reliable, and accountable.
Okay, so now for our novel notions segment, where we take the ideas from the paper and brainstorm some potential directions for future research, maybe some slightly out there ideas, but still grounded in the core concepts. What comes to mind when you think about this work?
Well, one idea that I find really intriguing is exploring this concept of dynamic calibration for CLM. Right now, they use a fixed calibration set to determine those lambda parameters, but What if we could make that process more adaptive?
Adaptive how?
Well, imagine a system that first analyzes the input prompt, maybe by looking at the number of entities involved, the types of relationships described, even trying to estimate the number of logical steps required to solve the problem. And then, based on that initial assessment of complexity, it dynamically adjusts those lambda parameters on the fly.
So instead of using a one-size-fits-all calibration, it tailors the calibration process to the specific challenges of the problem at hand.
Exactly. And the paper showed that using a more diverse calibration set led to better generalization. So a system that could intelligently predict the complexity of a new task and then adjust its calibration strategy accordingly could potentially lead to even better performance, especially on those more challenging problems.
It's like giving the system a bit of metacognitive ability, allowing it to reflect on the problem and choose the best approach.
Right. And you could even imagine training a separate lightweight model specifically for the task of estimating that problem complexity.
Interesting. So what's another novel notion that this research sparks?
Well, another idea that I think has potential is incorporating feedback from the ASP solver, Klingo, back into the CLM generation process. Right now, that rejection sampling process is based on those static metrics: quality, diversity, and confidence.
Right.
But what if it could also learn from the actual errors that Klingo throws? The paper provides this great taxonomy of the common errors that occur. So if Klingo is repeatedly failing to execute a program because of a specific type of syntax error, the CLM could learn to penalize similar program structures or translation patterns in its future attempts.
It's like giving it a way to learn from its mistakes in real time.
Exactly.
Yeah.
It would be a form of online learning within the problem-solving process itself.
And that could lead to faster convergence to correct solutions and potentially reduce the overall computational cost.
Right. You'd be avoiding those repeated attempts that produce unusable code, and that could allow the system to generate larger and more reliable conformal sets within a given computational budget.
These are really fascinating possibilities, and they really highlight the potential for further innovation in this space.
It's a reminder that research is an ongoing process, and there's always more to explore and discover.
Well said. So, to wrap up our deep dive into this paper, it's safe to say that it represents a significant step forward in enhancing the reasoning capabilities of LLMs, especially through this clever combination of conformal language modeling and answer set programming.
It really showcases the power of conformal prediction for providing those statistical guarantees, the importance of having a diverse set of examples in the calibration data, and the value of using evaluation metrics that are appropriate for the specific domain you're working in.
Absolutely. And while those challenges of generalizing to really complex reasoning tasks remain, this research lays a solid foundation for future work in neurosymbolic AI and the development of more reliable and trustworthy AI systems for a wide range of applications.
Right. And for our listeners who are keen to delve deeper into the technical details of their methods, the experimental setup, and the full scope of their findings, we strongly encourage you to check out the paper itself. We've included a link in the show notes.
And we'll leave you with a final thought to ponder. As LLMs become even more powerful, how crucial will these formal methods and statistical guarantees be in ensuring their reliability? Especially as we start to deploy them in real-world scenarios where the consequences of errors can be significant, like in healthcare, finance, or autonomous systems, that question of trustworthiness is going to become even more important.
It's a question that researchers and developers are going to have to grapple with as we move forward into this exciting new era of AI.
Thanks for joining us for this deep dive into cutting-edge research. Until next time.